All right. Hello, everyone. I hope you're having a great afternoon or morning or whatever time of day it is, wherever you are. Those of us at T&D World are excited to bring you this new webinar entitled Cable Monitoring Insights from Con Edison's Comprehensive Approach. This event is sponsored by Prismian and the Power Delivery Intelligence Initiative, or PDI Squared. My name is Rod Walton, and I am managing editor with Microgrid Knowledge and EnergyTech.com, which together with T&D World are part of the energy team at Endeavor Business Media. And I'll be doing the introductions and closing for today's event. This is truly a mission critical topic as power grids age and demand for reliability and resource adequacy grow. You're going to hear from experts with New York utility Con Edison and also worldwide cabling leader Prismian and its optical sensing solutions division. Your moderator for today is Mike Beeler, who is national spokesperson with Power Delivery Intelligence Initiative. Before I turn it over to our speakers, though, let me share a few housekeeping items to just help you participate in today's presentation in the most seamless way possible. First, if you're having any technical difficulties during today's session and you can hear me, just find the question icon and the links on the left side rail. Click those, type in your problem, and our technical expert will help you out. We recommend that you disable any pop-up blocking software or extensions in your browser, as these can cause issues sometimes with the webinar player. Your questions are welcome during today's event. Mike and the panel will answer as many as they can in the Q&A session that follows the main presentation, but please feel free to send those in at any time, and they'll get to them up to the top of the next hour. Just type them in, hit submit, and you'll be in the queue. Also, be aware that today's session is being recorded and will be available on the T&D World website within the next 24 hours. That's tdworld.com. You'll be notified by email when that archive is available. And we'll also make any presentations available by looking on the left side of the rail. If you want to share it on social media or access event resources, just click one of those icons. And that's all I've got for now. I'm going to turn it over for the main event and our moderator, Mike Beeler. Mike, it's all yours.
Thank you very much, Rod. Really appreciate that. Welcome, everybody. We're so glad you're here. I am with the Power Delivery Intelligence Initiative. What is that exactly? That is a group of contractors and consultants and cable manufacturers and equipment manufacturers that advocate a good close look at underground versus overhead. We hope and we want to provide resources for planners and engineers and even data scientists today to evaluate the total cost of ownership of underground versus overhead over the life of the asset. Think total cost of ownership over the life of the asset. So today, one of our board members is Prismian Company, and we're with Sergey Golostov from Prismian. And Sergey, I want to say a quick hello to the audience today.
Yeah, absolutely. Hello, everyone, and thank you for joining us today. Truly pleased to be part of this important discussion, joined by Ari from Con Edison, who will be leading today's presentation and sharing some practical insights from one of the most, I believe, advanced cable monitoring initiatives in the US. I'd also like to thank you in advance, Mike, for moderating today's session, bringing this expert perspective on the evolution of utility infrastructure. And at Prismian, and specifically within EOS, our mission is to help utilities transition from reactive maintenance to proactive maintenance, data-driven asset management. And this shift is crucial, I believe, for utilities nowadays. But it's more than just technology. It's really about mindset. It's about seeing what's happening in real time, spotting issues before they become problems, and making better decisions for the long run. And I'm proud of the work we're doing alongside innovative utilities like Con Edison. And I look forward to sharing how these monitoring strategies are delivering real impact across the grid. I'm happy to answer any questions during the Q&A, and so please don't hesitate to engage. Looking forward to a great conversation. Thank you.
Thank you very much, Sergey. I appreciate that. Ari Makovas from Con Ed, we're thrilled to have you here today. And Ari, just say a quick word of introduction, and then I'm going to say a couple words about what Sergey just talked about, and then we're going to turn it over to you. But Ari Makovas, say hello, if you would, please.
Yeah, thank you, Mike. Hi, everyone. My name is Ari Makovas. I'm a technical expert in Con Edison of New York. I'm personally thrilled, happy, and honored to have that time today with you. I can share whatever our company vision on the cable monitoring system and already some practical steps we took and we implemented already. I don't want to spoil more. We will talk in a few minutes. Thank you, Sergey, for very good words. And Mike, back to you.
Well, Ari, we are going to talk about cable monitoring at Con Ed. So Con Ed's got one of the largest distribution underground and a little bit of transmission underground systems in the country, if not the world. It's obviously a heavy urban environment. And so you guys have come up with some insights that you're going to share with us today on cable monitoring. So when we talk about the total cost of ownership over the life of the asset, it's not just the cost of the capital cost of putting in an underground program, the design and construction of the capital cost, but it's how's that underground system work for the next 50 years over the life of the asset. And at the Power Delivery Intelligence Initiative, we think that the total cost of ownership is less over the life of the asset. So today we're thrilled to have Con Ed come in. Ari, I'm going to hand it off to you, and you're going to take about the next 35 or 40 minutes explaining to our audience today some of the cool things you're doing. So with that, Ari Makovas, Con Edison, go ahead and take it away.
Thank you very much, Mike. Thank you. So again, my name is Ari Makovas, Con Edison of New York. I'm a technical expert in the company, and I would very proud to work with that company. Just want to share with you some news. Maybe some of you doesn't know that, but the company celebrate in 2023 200 years of existence. So basically, we've been created in March 26, 1823 as New York Gas Light Corporation. You see picture on the right top. This is New York Gas Light Corporation crew on a chariot ready to go on emergency service. You see that nice picture. About 60 years later, in 1882, Thomas Edison started up his electric generating station in New York, and from that moment, we also serve electricity to New York City. Today, our company providing and serving three different commodities to New York City. It's the gas, electricity, and steam. On the bottom right picture, you see in 2023, our executives in New York Stock Exchange celebrate the 200 years of our company. Another interesting fact that one of the five companies who founded New York Stock Exchange and still under same name, the part of New York Stock Exchange. So now I want to share with you what our service territory. So we basically serve 604 square miles, 1,564 square kilometers. This is our territory. It's 3.6 million customers here, and more than 13 gigawatt peak record of electricity supply. We have 103 area and transmission substations. In 2022, we supply 52,000 billion kilowatt hours of electricity. Reason for that slide is just to show you how small the territory. If you look on New York State, New York City, which is 5 boroughs, Manhattan, Brooklyn, Queens, Bronx, Staten Island, and Westchester County, this is very small dot in the bottom of New York State. If you divide 13 gigawatt by 604 square miles, you get 2,000 megawatts per square mile. This is very electrically dense area, heavy populated area, and that's also dictates certain approach what we use to manage our system, because in this system you don't have too much flexibility in terms of shifting load, shifting power, and of course not even a question to shed loads. So now we will be focusing on our the transmission system at the backbone of our power system. The transmission system mostly underground, so we have 754 miles of underground circuits. It's 1,213 kilometers. Total number of feeders are 389, mostly pipe type, about 80%. Oldest feeder, average age is 48 years, and oldest feeders, today it's 76 years old feeder, still in service and will still many more years. That's also important, and it's one of the factor why we're discussing that today, because it's always the question come, what is the lifespan of the underground feeders? When you need to start to worry of life expectancy. We also have 569 miles of overhead circuit, mostly come from north and ending up in Westchester County. That's 569 miles, it's 51 overhead lines. For underground system, we also have 125 pumping plants and 76 cooling plants. So you can imagine how hard to manage that system, especially in a heavily urban area, and constant question what we're getting from our executives, from regulators, uh, um, why that feeder must be replaced, why that feeder must be repaired, why you have this or that on your system, how it's affected by the age of the system, or what is your asset management plan. So for pipe type feeder, for many years we have the asset management system, but we start installing solid electric feeders recently. Basically, we starting from 90s. We increase our system in 2000, but right after COVID, with implementation of new green renewable power act, we start put more and more solid electric system, and we want to develop cable monitoring system, which can basically help us to manage our solid electric underground system, and also will help us to correctly assess their condition. And also we understand that in the future, we most likely will have very soon artificial intelligence involved in data analysis. And for data analysis, you need data. To acquire data, you need sensors. So you basically need to have system right now, at least from perspective of acquire data array. So then in the future, very near future, artificial intelligence or any other methods can help us to correlate the data and see relationship between different parameters. And basically, after you press the button, can help us to understand what's the condition assessment of particular feeder and what the course of action we need to take. So when we analyze, before we analyze what happened in our system in, let's say, last 20, 30 years, we see some of the cable failure happened in the vicinity of heavy traffic area, substantial elevation differences, ongoing construction site, or near external heat sources, steam pipes, subway, other transmission circuits, or distribution circuits. Fault locating effort may take relatively long time because in the urban environment, we install our system in the duct bank, in the duct, basically, underground. So we're not allowed to dig everywhere to get access to the cable. We only have access to the walls. And that's why fault locating may take sometimes a long time. Mandatory routine inspection of underground walls. That's mandated by regulators. Every 5 years, we need to perform structural inspection of underground walls, and that's also take time and labor to do. And of course, asset management program. We need to know condition of our assets in order to act proactively, not reactively after something already happened. And especially now, then we to transform our system completely and use more distributed resources, implementation of wind and solar power, installation of solar storages. That's all will change the system. From one side may shave the curve, but from other side may reduce time for cable to cool, for example, at night, right? So that's all changes. Asset management or asset system will play more and more role in everyday decision. So we decided we need cable monitoring system. First question came, okay, what project we will use as a pilot? So on your screen right now, you see project which was chosen in 2016 as a pilot. It's 5.7 miles, 9.2 kilometer concrete duct bank, single circuit, 17 underground volts, operating voltage 138 kV, XLP insulated, 3000 kcmil conductor, it's 1500 square millimeters. The ground continuity conductor 500 kcmil, also XLP insulated, single point bonding scheme. And we also use fiber optic cable in separate duct for partial discharge and DTS system. That was and still our standard. And that project was chosen as a pilot for installation of new cable monitoring system. So next question came, how we describe that system? What's the description of the system we're going to address? So the cable monitoring system design combines two potentially separate operational workflows into a single integrated system. So we try to address two in one. From one side, assets health parameters typically associated with an asset condition. For example, temperature, for example, partial discharge, right, or the current in the sheath. And second, it external operational parameters related to what asset often used for periodic inspection, for vault inspections, or for route patrol to see if anybody digging or working near our system, to address security measure if somebody trying to enter to underground vaults, and also to find out failure. If sometimes failure happened, you need to find it. So we try to combine those two completely different approach, asset health parameters and external operational parameters together in one system, try to address complexity of the situation, and also trying to justify the budget component of the system, right? We need to have funds to install the system. So if we're doing anyway underground walls inspection, we pay for it. If we're doing anyway fault locating, we pay for it. If we're doing anyway route patrol, why we don't take same funds and combine them into the system cost? That will help to justify the cost or even minimize the cost of the system. So now we're coming to really important slide. What's the requirements of the system? What are we looking for? What sensor should we install? As I said before, we find out that any abnormalities in a system happened during some events like heavy rain, storm, or near the busy intersections, heavy traffic, near heat sources. So that's what dictate what sensors or parameters we're trying to put into that system. So first, of course, we look for partial discharge sensors. I'm sure most of the people knows what it means on the call, but just a few seconds to explain. Full discharge is from conductor to the ground. Partial discharge, any not completed discharge between. Somewhere in insulation in the middle or close to conductor or close to shielding, any voids, any imperfection can create temporary discharge, which may not affect on anything if it's alone, but if it's a lot of them and start happening routinely, may damage insulation or reduce insulation strength. And that's what can start happening and eventually will lead to the failure. So partial discharge, we see as an important part of the system. How important is that? When you energize the system, we believe it's important to do partial discharge reference scan, just to have the uh, baseline for your future analysis. It's the same thing like a person, young person coming to doctor and do EKG. And then every 5-10 years, repeat that EKG, and doctor can compare and see if any changes going on. It doesn't mean you need to rush and go on a surgery table right away. Of course not. But it will early indicate if something going on with your system. Same thing with partial discharge here. If you have your baseline for your joints and terminations specifically, and if it's possible for your cable, and you have baseline when you energize the system, and then you can every 5-6 years periodically check it, or if you have online system, you see it online, any change in behavior of partial discharge, free parameters, repetitive rate, magnitude, and correlation with your major the power signal. If one of these parameters change, it's already can give you indication. Next sensors is shift current monitoring. Why is important? For transmission system, we want maximum rating for the cable. So maximum rating, which is no heat sources anywhere around. So you don't want to have circulating current in your sheath or in your shielding of your cable. Because if you do, this is a heat source right here, right on top of your cable. That can reduce 10-15% of ability, that conductor size. So that's why we install single point bonding system. But we need to understand, is it really no shielding current here, or some current occur, especially if you use cross bonding system or anything else. So shift current monitoring system, absolutely not expensive, very simple system, can prevent uh, um, much more significant event when you can have overheated cable because of the significant current in the shielding. Temperature monitoring system, DTS. Of course, we know DTS for a long time, and we use it for different reasons. For cable, for power cable, DTS will play several roles. One, to monitor appearance of a new external heat sources. We cannot monitor what happened on the street all the time. People or other utilities, other entities can install different system, can install some ventilation from the subway, for example, in New York City, can install additional power cable, and those heat sources will appear on the profile of your feeder. And then you can basically investigate, see, or you can adjust your maximum rating, especially when we're talking about transmission, purely transmission feeders, when load can go either direction, connecting bus to bus. Those feeders, sometimes you need to use to the maximum of their ability. Doesn't matter for 3 hours, for 20 minutes, or for 300 hours. We're using one of the parameters in our system, 300 hours. And where is those 300 hours come? Very simple. It's a time, it's a 2 weeks needed to replace transformer. So yes, we will overload that feeder for 300 hours. We need to know, can we do it or not? That's how important that system is. Potentially, it can develop to the dynamic feeder rating system in the future. So basically, operators may see every hour change of temperature, if it is, and they can put more power. We all know the thermal environment doesn't change quickly. It may take several days or probably several weeks. So that's basically the very good opportunity for operator to take advantage of that time and put more power. Also, we planning to use DTS system to monitor joint thermal condition. We all know joint, it should be kind of heat sink, coolest part of the cable because of the size. But in reality, it's not exactly the true, because in the summertime, because we install them in underground walls, temperature in the joints can be higher than ambient temperature of the soil surrounding the feeder. We also planning to already installed video and infrared stream access, stream cameras. It sounds amazing, but today IP cameras became relatively not expensive. They can easy to be switched from infrared to regular mode. And we're doing that primarily for few reasons. One reason, to perform mandatory vault structure inspection. Today, we perform inspection by running two crews of two people in the streets. They blocking the traffic from both sides of the underground vault. They open the vault, they clean it, and they take insulated stick with a GoPro camera and do structural inspection. They're looking for any damage to concrete, any damage to cable supports, any other structural damage. We mandate to do those inspections, and that's take them probably 2 volts per day for these two crews, sometimes even one. So if we have those cameras installed inside, you can save the time and do all 17 volts in one day from your desktop computer. So we also can perform joint infrared inspection. That infrared inspection will help us to understand if it's any overheating going on with the joints. We know over life of service, cable joints experience different forces, and also that may lead to movements may lead to some physical damage, small damage, but that small damage can start overheating locally, and infrared camera can help to find it out. And also the cameras can address security concern. Basically, you can if somebody wants to enter the manhole without authorization, you will see live video footage of it. Also, we plan to install vibration and displacement sensors. Vibration sensors is for DAS system or DAS system. It's a very well-known system for submarine cables, for military, right? So you basically can monitor vibration in the area. That can help us to address routine patrol over our feeders to see if anybody using air hammer, piling, digging in the vicinity of the feeders. Strains specifically for those operations can be put in the system, and you can see and you can send your crew to verify what's going on your system. It also can help us to locate the cable fault, because when we put each individual phase in a different duct, when failure happen, especially single phase to ground failure, it's going to be huge electromotive force, and that cable will jump in the pipe, create significant sound strain, and fiber can detect it. And basically, right after the failure, next few minutes, you already know where the failure is, how many feet from each manhole. To monitor effect on the traffic vibration. And also we will install displacement sensors to monitor joint movement. We know joints should not to move, not supposed to move. However, it's moving sometimes, which leading to the joint failure. And that's what we're trying to monitor. So these sensors, we're planning to be part of the comprehensive cable monitoring system. Next question, what required infrastructure for the system should be? Of course, specialized electronics for the data acquisition and communication, specialized support for sensors and electronic enclosures. That's first system what we used. We used a lot of enclosures, and we learn in a hard way, probably it's better to have sensors which can be submersible. Safety, the grounding and the bonding for electronics and enclosures, power supply for electronics. We try use batteries. It doesn't work very well. It's create more problem than solutions. So we're using power, 120 volts power supply. Communication channels, additional space in the wall. That's what needed, right, for maintenance and for installation. Connection to corporate network. That's another very painful point. all systems should be cyber secure. All systems should be connected to corporate network in order to have access from anyone in the company. We also need additional servers for the data storage, because you remember, major idea is to collect data. So what's the installation requirements? It should be robust and low maintenance. Submersible IP68, then we change it to IP69, then we change it to NEMA 4. Now we have NEMA 4 plus 15 feet of water column, 48 hours test. We do test before we install that system, because we find out with all these hurricanes, rain, and other weather events, some of our manholes, not all, but some of them get flooded. By the way, we have approximately around 2,000 transmission manholes and dozens of thousand distribution manholes in our system. We need to have sufficient light for camera inspection. If manhole completely closed, it's dark inside. When you light up the camera, that light, when you see it's on the top of the camera, may create reflection for the camera. So we solve it differently. We replace this light with something else. Low voltage power supply we must have in each manhole, and indication of power loss, so we know if power loss, we must have indication right away through the system so we can come and fix it, and 15 minutes at a backup for power supply. And this is also power and communication requirements. We decided it's going to be 120 volt AC, 30 amp in each volt, and the same thing in each substation end. You can see here on the picture live connector in the volt, which can be submersible. When you cap it, it can be submersible. When you uncap it, you can basically use it during installation, and also been used for the system for system operations. We also have robust grounding system in each manhole. We installed 2 fiberglass reinforced epoxy conduits for entire feeder route for fiber optic cable. I know in the market many cable suppliers provide fiber optic as a replacement one of the individual wires in the shielding. We don't in favor of that technique. We always request fiber in independent duct. It's not a topic of that discussion, but we learn in many years what's the pluses and minuses, and decided to run fiber in separate duct. So we use multi-mode and single-mode fiber optic cables for entire feeder route. Multi-mode we use mostly for communication and data transfer, and single mode we use for DTS and DAS for more precise measurements. So cybersecurity requirements, that was a very robust requirements from our system. So we perform hardware security scan for each network component and for each sensor. For each processor, we perform cybersecurity check. So application and software security scan. All security scans performed prior to system commissioning, check after already every single component being checked, and now you check entire system, you check all the ports. We don't like two-way communication, so that's all ports will not use, should be closed. All system access block must be locked and located inside utility properties. We install it in substations, and after we do final cybersecurity scan, no one can touch that server. So and special the permits must be obtained to perform any work, update, patches, or whatever we do for the system to keep them alive. So this slide you see in the middle, you see rendering of the underground vaults. It's easy to see all components together, and you can see here 7 pictures around actual pictures in that vault. So let's go over that. So originally we installed 2 boxes for the system. Now we're using only 1 box. Third box is a link box. Link box is part of the grounding system for the feeder. You can see 3 vertical installation of the single circuit solid dielectric system, 3 joints. You see supports, and you can see camera on the left corner. This is the camera pointed to the left side of the supports, another camera to the right side support, and middle camera pointed to the splice. The middle camera normally we turn on as a infrared camera, but it can be turned remotely to regular camera and also do this regular visual inspection. And you can see here on the left side, when my cursor right now, this is local vibration monitoring sensors. In addition to fiber, we also install local vibration sensors just to validate what we have in the manhole, in the vault, sorry. Then you see here technician basically performing the calibration of the system, same thing on the bottom. On the right side, you see cameras with a submersible enclosure installed there. Very important for fiber optic system by itself, because we run fiber optic system in separate duct to support cable monitoring system. When we come to the manhole, we use 25 feet coil up in the corners. I think somewhere here I saw the picture. I just want to come back for a second. Right, you see here on top of camera, it's 25 feet coil fiber optic cable from both sides of the manhole. It's done just in case we need to do repair, or if its failure happened and fiber will not be damaged here because it's separate, so we can resplice it. It's number one. Number two, for DTS, it's help us absolutely identify where is the underground walls, because we see those 2 coils clearly. And for DAS too, we basically know exactly where is our underground walls. That basically shows the system itself. Now, next picture shows installation, calibration, and commissioning. So what you see on the left side, this is the view from the camera, from the system, view from camera on the joints. You see joint supports. And picture below, left bottom picture, this is camera turned into infrared. Same view, infrared. You see hands of the splicers, which basically shows this is the temperature of the human body around 36 degrees C. And you can see the much cooler temperature of the joint here. And this is we did during calibration. That's why you don't see any heat from the cable. It's not energized yet, but we calibrate the cameras. Middle top picture, you see truck and you see person with a hammer trying to release that hammer from 6 feet high to the vault hatches. Basically, they created the very distinguished the sound effect. You can see here the system found it. That's how we found all the underground vaults by that calibration. Right bottom picture, you can see entire profile of the feeder. You see the vibration profile. You see some peak here in the middle, right? And you see here that peak shows on the map. Basically, this is a traffic vibration, mostly traffic noise. Same picture I made from this system. You can see train. We have several train, railroad passing on top, and you can see when railroad passing, you can see those trains. So we know based on vibration profile, we have 3 railroad passing, we see major intersections. So we see those heavy vibration, constant vibration happening, and we try to monitor them. And I explain in a few minutes why. So basically, that's what we installed. We installed and energized that system in 2019. We installed partial discharge monitoring, DTS monitoring, DAS monitoring for fault locating and construction activities. We install video and infrared vault inspection. We install camera, video, and infrared cameras. We install local vibration monitoring just to validate what we have from the fiber optic cable, because it's kind of like diverted from the cable itself. That's why we install them on each cable, top, middle, and the bottom. We know vibration in the volts, it's higher than vibration along the route because it's exposed to air and because we have hatches and it's in under heavy traffic area. We also install volt entrance alarm. So basically same fiber acting as a volt entrance alarm. Okay. There's a picture of the complete system from substation side. You see the rack with partial discharge, DAS, and all other system. You can come here, you can log in, you can get all information from there. You can see live feeder, infrared on the bottom picture. You see this is from infrared camera. You see now it's a different color because it's a different temperature, and you see supports has a higher temperature than basically cable itself. And this is a video how you see from video camera for inspection. You see water covering almost like half of the bottom cable. You can see all support from one side and from another. The benefits, partial discharge is particularly useful in monitoring health status of the cable and will be used for assets management. For assets management. DTS monitoring system will measure the cable condition, temperature, and will help to develop cable rating based on actual condition. DAS will protect cable system from future construction activities and will help to quickly detect the cable fault location. It will also eliminate need for the transmission route patrol and increase awareness of any construction activities, the digging, piling, sewing on, or anything else. Visual and infrared cameras installed in each vault will allow for simple remote vault and splice inspection, significantly reduce time for inspection and safety concern due to remote inspection. Displacement sensors, together with local involved vibration sensors, will alert engineers on splice movement and will generate proactive maintenance activity, preventing potential splice failure. Shift current monitoring will ensure that the grounding of the cable system remains intact throughout the life of the system. Overall, this system will provide both operational and asset management parameters and will create valuable data for future use of machine learning algorithms and artificial intelligence. And we believe that system will provide the basis for improvement of the cable system design and installation. But most important, we see that system, AI and machine learning algorithms can help us to correlate between different parameters. For example, how the vibration, increased vibration strain can affect on partial discharge, how the temperature increase can affect on partial discharge, or how the current, increased shift current can affect on the cable performance and other parameters. So that's a major benefits, correlation between different monitoring parameters, and that will provide the basis for improvement cable design as a cable system design, installation and maintenance techniques. So when you see correlation between different parameters. I came to my last slide. So basically, in conclusion, first project was tested and energized in May 2019. Second project with modified cable monitoring system was tested and energized in May 2023. We now installing generation 2 of cable monitoring system, and we working on generation 3 of cable monitoring system. We shooting for complete fiber optic sensors for everything. We're trying to eliminate electronics from the underground vaults, which also eliminate the AC voltage in the manhole. The cost of cable monitoring system, it's incremental in comparison to cable system material and installation cost. It's much less than 1%. And we hope that that system will provide valuable data. And we believe this is the first step to the asset management of the future more reliable underground system in New York City. Thank you for your attention. And Mike, back to you.
Thank you, Ari. That was fascinating. And I'll tell you what, I just had all sorts of questions as we went along. We have some great questions from the audience as well. So let's start to delve into those questions right now. And I will say, Sergey, if you want to add to this as we go, but I want to go back to the very beginning, Ari, but also to the very end that you talked about what you're going to do with artificial intelligence. So you said at the very beginning, you basically said artificial intelligence needs data, and you got to have the data from the sensors. You said these sensors have got to be submersible, they've got to be connected to the corporate network, they're going to be powered by the 120 volt AC power source. Had some questions about where is that power source coming from? What kinds of sensors are you using? So can you go back, Ari, and just talk to us a little bit more about your vision for how you're going to use artificial intelligence and some of the technical part of what kinds of sensors you're using, how are they installed, where's the voltage source, etc. And then, Sergey, if you want to jump in there as well.
So the sensors, what we installed, they powered by 120 volts, 30 amps circuit, dedicated circuit. We run that circuit from above ground pole or from distribution manhole, low voltage manhole nearby. So normally it's like not more than 10, 20, 30 feet away from transmission manhole. We have a source, we run the duct, we run it inside, and we have live connection inside the transmission manhole. That's a source of power. Of course, that power come to power electronics, and from electronics, it's come to sensors. That's how we power the sensors. How we install the sensors, of course, partial discharge is simply the current transformer connected with coax cable. In the future, we believe it's going to be more fiber optic sensors to check it. But right now, this is CT transformers. For vibration, is vibration sensors or displacement sensors. It's various sensors available in the industry. When we started, of course, we found what we found. Now we're much smarter. We know exactly what's suitable for us. And some of the sensors originally required special enclosures. So now we're trying to install sensors which not require enclosures. That's
so
all.
Is it correct to say that this is a pilot program that you did in 2019 and 2023, and that you still now what you've learned on this you're going to implement across your 389 underground feeders, or are you already putting this onto many of these feeders?
No, it's a very good question, by the way. So no, we're not going to implement for 389 feeders, but we're installing for every new circuits for the same reason why we cannot implement it for 389 feeders. We cannot because, like I said before, in heavy urban area, very hard to get prolonged outage for the system. Yeah. Imagine to install that system on existing feeders, let's say 15, 20 underground volts. It's a month of outage. And that's
I was having a hard time. Yeah, that's extraordinarily challenging.
That's impossible in our territory. So we decided we're going to install it on every new project. And during construction, we're installing that system, and we must install it because we will not have second chance to install that system. We may have second chance to improve the system. We may have second chance to maintain and repair the system, but we will not have time to install it.
Right. And you made a decision that you're going to use fiberglass conduits for your fiber optic cables. So you're running a couple of cables for fiber optics, and they're going to be fiberglass. Why? Why are you going fiberglass?
So I know in the country and in the world, people using for high voltage cable, polyethylene pipe, PVC pipes, concrete ducts, and we use fiberglass reinforced epoxy conduits. Why? So, and also people use metal conduits, of course. So we experienced some early failures, and we find out if duct for the cables are polyethylene, same material as a cable jacket, when failure happened, the polyethylene jacket can be melted and bonded with the polyethylene pipe.
Mm.
And then will be very, very hard to pull it out. That's number one reason. Number two, polyethylene is a high thermal resistivity comparing to other materials, and it's also effect on rating calculation. So, and third one, same material on same material, it's a higher coefficient of friction. So those three parameters, that's why we don't use polyethylene. Of course,
Well, that was a question asked by a civil engineer, me, but that's a great answer. Those are three really good reasons.
Understood. So PVC, we installed PVC for 70 years. I mean, in the past, and after many years in the dirt in New York City environment, when anything will going but not water on the ground, so we find out PVC dry out tremendously. Corrugated, dry out, and in some instances we found PVC 70 or more years old. You touch it, is basically gone as a powder. So that's why PVC is not good for us. Plus, we committed do not use PVC inside substation because in case of any fire, they produce chlorine gas. It's polyvinyl chloride. That's what PVC stands for. So that's why we use fiberglass reinforced epoxy. What is that? It's basically when they produce, they're using kind of like a dummy, and they pour like a fiber slinkies around it, and they pour or brush epoxy. So it's very, very light. One person can lift 20 feet of pipe easy.
Right.
And it's very light. It's basically glass inside. So when failure happened and we interrupt transmission failure in 3 to 5 cycles, it's not enough time to melted jacket stick to that surface. Plus, coefficient of friction very low, even without lubrication. So that's a pluses. Of course, minuses. It's must be cast and it cannot be bended. But PVC also cannot be bended. Only polyethylene can be bended. So we check all of these parameters, and we decided we're going to use fiberglass reinforced epoxy (FRE) conduits in casing concrete.
I can
yeah, go ahead, sorry.
Yeah, I just wanted to very quickly add on the first part of the question about artificial intelligence. It's really harder to say better than Ari that to benefit from AI, you need to have data, and to have data, you need sensors. And what I love about the Con Edison approach, it's that is holistic, comprehensive, and they put different systems in place, and then they are trying to correlate data between different systems, and sometimes that they can be very interesting and unexpected discoveries from that. But obviously, to do it, you have to be kind of a pioneer and try things out, and then let's see what happens. And I'm really happy that Con Edison is the company that is courage enough to do that, and they will be probably the first to benefit from it. Yeah.
You know, Sergey, and that leads to a couple of questions that I was going to actually send your direction about. You know, Ari talked about writing algorithms against this data, this new source of data. Is that something that Con Ed is doing internally with your own data scientists, or is that something that they turn to a company like yours to write the algorithms to produce that extra value that tells me what the vibration and the temperature really might be doing to impact my cable? Sergey, what are you guys doing that at Prismian, or Ari, or are you guys doing that internally?
If on my side, I can say that normally with Con Edison and also with other companies, it's kind of always collaboration. So there is a significant part that vendor does and proposes to the customer. There are some customers that do it on their own. I think that's very collaborative because data should be accessible in a certain way. And yeah, I think, I don't know, Ari, what path would you take? And I think I'm very curious also to hear that. But normally it's more collaboration between companies rather than one part doing everything alone.
So it's very well-known companies on the market who do partial discharge, DTS, or anything else analysis. So of course it's collaboration. We tell them, Con Edison will tell them, our team, we create scope of work, we tell exactly what we want, how we want, and those vendors can implement that in their software. And of course we check it, we calibrate. That's one of the reasons why we install various sensors, which in some instance basically um, shadow each other. For example, local vibration shadow the DAS fiber in the vault. Just example as that. So we can have data from different type of sensors, same parameter we can see, and we can validate how accurate they are, because DAS software says they can measure vibration strain every foot, right? We would like to validate that. We would like to see in a practical thing how it works.
So, Ari, I've got a last question here from the audience, and it's really one of the questions that I thought was pretty cool as well. Have any faults been detected, including the fault location, using the two systems that you've already installed? You said you have the ability to do fault location to within feet. So, have you in fact detected some faults using the new system that you put in?
Luckily not, because we just installed in 2019, and thank to our engineer and robust system, we didn't have failure on that feeder. We just started that. However, we find out some partial discharge during the commissioning test. We find out some incorrectly installed surge voltage limiters, and we found it through the shift monitoring system. So yes, we see some benefits already.
Yeah,
Great.
I can only
But
add, Mike,
yeah,
that luckily not all the cables fail. So it's also a question of statistics. So basically, if you have cable fault monitoring system placed for many circuits, so eventually one day you will benefit from it. And for example, we have an experience not with Con Edison, with another company, that we were able to help them to detect the location of the failure on the cable, not on the joint.
Yeah, gentlemen, judging from the number of questions that we still have, I think we got most of them covered, but this topic is fascinating, and I really appreciate both of you coming in and talking about it today. I think it's a real service to the industry. I'll tell you what, let's just wrap up. Sergey Kolostov from Prysmian, why don't you give us some concluding remarks here in this last minute or so?
Yes, absolutely. So thank you all for joining today's session. First of all, I believe it's clear that proactive data-driven monitoring is key to the future of the utility management, and I'm excited to see how these innovations continue to shape the industry. A big thank you to Ari for sharing this extensive expertise with the industry, to you, Mike, for helping us out today, and everyone involved in making this event possible. And I believe we are looking forward to answering your questions and continuing the conversation beyond this this session. And thank you again, and have a great day.
Thank you, Sergey. We certainly appreciate Prysmian's involvement in this webinar today. Ari Makovas, you have done some fascinating things at Consolidated Edison. You've got a couple of, I guess we're going to call them pilots going here, that are really fascinating, and you're learning a lot that you're going to now deploy on every new circuit that you do in your service territory. Give us some concluding remarks. In comment, I think one of the things you said towards the end there was that the cost of this whole system is less than 1% of the capital cost of the underground program. It sounds like a less than 1% of very valuable way to spend some money on this project for the longevity of the system. So give us your concluding remarks, Ari.
Thank you, Mike. Thank you, Sergey, first for inviting me. Thank you, Mike, to help us today. I'm really thank you for everyone, for audience to listen to us, listen to me. So I want to say that I'm so fortunate to work for company who support innovation, who find out a way to do R&D in that area and just implemented that. And I'm very fortunate in that. So with that system, I truly believe we'll address some of the issues in the future, and that system will make our the grid in New York City more reliable, more resilient, and ready for any challenges in the future. Thank you.
Well, thank you, Ari. Here are the email addresses for Ari and for Sergey if you'd like to reach out to him. I'll tell you what, this sounds to me like, Rod Walton, as I get ready to hand it back to you, it sounds to me like this needs to be an article in T&D World Magazine. It's a very interesting topic. I'll look forward to hearing you at IEEE meetings, maybe the big PES or the next Distributech. That is a fascinating topic. Appreciate both of you gentlemen today coming on board. And so on behalf of the Power Delivery Intelligence Initiative, we say thank you to the audience for listening in today. And with that, Rod, I hand it back to you.
All right, Mike, thank you. And it was a great presentation. Great job, Ari, and some great remarks there at the end by Sergey. Would make an incredible case study for sure. But I'm afraid we've run out of time for this webinar. I'm just so glad that you all could join us. And for our audience, please remember to take our exit survey if you could. Just a reminder that this event has been recorded and will be on demand within 24 hours. And it will be available for about 6 months after the live event. So please feel free to and welcome to share it with coworkers and friends in the industry. And we appreciate it when you do that. So that concludes today's presentation on cable monitoring insights from Con Edison's comprehensive approach. And thank you to our sponsors from Prysmian and the Power Delivery Intelligence Initiative. Great job, our moderator, Mike Beeler at PDI Squared, and Ari Makovas of Con Edison, and also Sergey Golubtsov of Prysmian. You guys did a wonderful job today. And you can just tell by our audience questions that they were really into it. And I want to thank our audience for attending and for those questions, because we all do learn from each other. Once again, please take our exit survey to help us going forward. And with that, we're going to end our webinar presentation today. I'm Rod Walton, Managing Editor for EnergyTech.com and Microgrid Knowledge on behalf of T&D World, which is the industry's media voice for the electric transmission and distribution sector. Thank you again for joining us. Hope to see you on an upcoming webinar in the very near future. Have a great day, everybody.